This is known as the line integral. But the word line integral really is like, it's more like a path or curve integral. Say there's some kind of quadratic surface like this, and this equation was given by z is equal to f of x and y, which I called u in my program that I just showed you, right? So let's say it looks whatever, something like that. Then let's say there is the vector function in xy plane, not in 3D, but two-dimensional vector function in xy plane that runs something like that in that direction. So this is the starting point, and this is the ending point. Good. And let's say that vector function is given by some kind of parametric equation. You still remember vector functions? Some kind of parametric in x, I vector, plus some kind of parametric in y, and j vector, that vector function. So far, so good. So what we want to do is evaluate this integral. This is known as a line integral on the curve C, and C is described by this vector function. So this is curve C. And this is where t is equal to a, and this is t is equal to b, okay, from a to b. And if we put f of xy, our quadratic surface, two-variable function, and put ds, what does that mean? And what does it even look like? How? I mean, we have done double integrals and even triple integrals, but that was over volume. How do you do it over line, right? Let's just review what integral was last year. So here's a curve. Here's a point A to point B, right? We are essentially integrating this thing along this x-axis. You know what I'm saying? Or we could have done it in y-axis, and we have done that before. But now we are trying to integrate this thing along that curve. What? What the? Right? What does it even look like? Here it was last year it was the area right there, that area under that curve, right? So what does this thing even look like now? I tried to sketch this thing very, very carefully, okay? Say if I go up vertically and then let's say it pokes the hole right there, right? And then this thingy, say, creates some kind of picket fence like that. Can you imagine this picket fence? It gives you the area of that fence. Picket fence, that doesn't look like picket. Photo wall along the US-Mexican border. Whatever that is, if you have a curvy fence or wall, it gives you the area of that thing. Oh my. So now we can visualize what it is that we are doing, right? All we have to do is now mechanically figure out how to do it. Okay, I'm gonna erase this now. So how can we evaluate this integral? We have to convert it into single variable somehow, and one thing we do is f, x, and y, according to this vector function, we can plug this thing in so it becomes a function of t. You know what I'm saying? And then we have to figure out ds. Ooh, what was ds? Do you guys remember what ds was? Arc length ds, that thing. Square root of dx over dt square plus dy over dt square dt, that ds. You know what I'm saying? So that goes in here. So after that, this is all said and done, and hopefully it's not that ugly. Everything is function of t from t is equal to a to t is equal to b. How about that? Okay, and as if that's not really complicated, we have, this is just actually a lot simpler than you think to do it, understand it. The other one that is more difficult to understand is the vector function. And vector function is your tornado, right? So say you have done tornado, and then you have some kind of vector field swirling around, right? Let's say this is part of your tornado, right? It's given by f of now vector field, let's say xyz. Let's just put 3 variable. Why not, right? Because you did tornado in 3D, right? Your x component, y component, z component. You know what I'm saying? Yeah. And they're all function of 3 variable, isn't it? P, let's say x, y, z, I vector plus q, x, y, z in j vector plus r, let's say x, y, z. You didn't, a k vector, you didn't enter it in this format, you put it as a column vector, correct? Your function x, y, z. In UCalc, my program, it looked like this. And then this, you had like y starting with blah, 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 and then negative x, blah, 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 z, blah, blah, ugly, ugly, ugly expression. You know what I'm saying? So this is P, this is Q, and this is R. So you fully understand what this PQR means, right? Because you have done it. That is, if you didn't cheat and copy somebody else's. And see, this was the motivation to make you do tornado project way early so that you understand what's going on here. Okay, if you release some particle here, then it's gonna fly, right? But suppose we build a track. So this is like sailing idea. Here's a wind and you wanna sail, not exactly along the wind, but as some kind of path using that wind on your sail, okay? So suppose you have a vector function that goes maybe like that. And that's curve C, right? So this vector function is given by R, and then you have x sub t I vector plus y sub t j vector plus z sub t k vector is a vector function. Okay. Now, what is the work done on your spaceship by the solar wind? You're basically using this vector field to sail in that path in 3D or 2D, whatever the dimension. Right? Okay, we'll do it. So, do you remember work dw is f dot dr? Okay, f dr and cosine theta. You want me to draw that diagram for you? Why that is? Work is force, displacement, and cosine theta. Okay, I think I need to draw that diagram somewhere. Okay, let's blow this part up. That part right here. Say your your displacement is going that way. This is dr vector. And then your field is going this way. This is F vector field, right? The wind of your tornado. And then what we have is that angle, theta, right? And not all of this force is doing the work. This is that component, which is a cosine theta component. You get it? So that is F cosine theta times dr. You know what I'm saying? Okay. But then that is a nice way, right? Because that's what we know as f dot dr. You see how that works out? Okay, this is very nice because remember f is a vector. All you need is a dr vector then, eh? Yeah, let's figure out dr vector. What is dr vector? Derivative of this, right? Dx over dt. Is that too small? Let me zoom in. I vector plus dy over dt, j vector plus dz over dt, k vector, isn't it? Okay, so now we'll take a dot product. So here your f, remember f has this three variable functions in it, p, q, r, and then you dot it with dx over dt, dy over dt, and dz over dt. That's what f dot dr looks like. Yeah, it's not really making that much more sense now, right? So what we have is the integrand is p. What you have to be careful is everything is in terms of t. So whenever there's a x, y, z, you have to take this thingy from vector function, parametric, and you have to substitute it so that everything becomes a function of t. So this is p sub t times dx dt, and dot product you add, so q function of t dy dt, and you add your r, which is function of t now, because x, y, z is all function of t, and then dz dt, and then take dt. You know what I'm saying? So your work done by the field along this curve is f dot dr, like that. Heavy, isn't it? Let's take an example to make this thing a little more sense, right? Yeah, because right now you have no idea what is that theory that you're throwing at us, right? Okay, example. Say there's a vector field, gravity, okay? Gravity. So extremely simplified version, so mg, negative mg times k. That's the vector field. Good? Okay. So it's just a vertical downward, right? Constant gravitational field. Now, say we have a vector function like this. Let's take Stairway to Heaven. Cosine t, I vector plus r, sine t, j vector plus, I'm going to put h over 2 pi, t, k vector. Why would I want such a thing, right? Okay, here's why. I'm going to draw the coordinate axis and then tell you what I mean by that. Oops. Say there's a coordinate axis and my vector function is gonna start from here at r, point r, this is r, right? And then spiral upward like that. You know what I'm saying? This is my curve C. Okay, if I just put t here, then this height, the vertical motion, this height will be just 2 pi, wouldn't it? Because t will vary from 0 to 2 pi. You know what I'm saying? I don't want this thing to be 2 pi. I want this thing to be h. That's that h looks like n. You know what I'm saying? So that if I put h over 2 pi when I substitute 2 pi, that gives me the height of h. Okay, so far so good. Say yes. Okay, now we have to decide, is it upward motion or is it downward motion? Don't get mixed up on that. I mean, physics book always throw the negative sign. So if you have to do the work, we are going up against the field. If the field is doing the work, then this thing will come down. You know what I'm saying? You know what I'm saying? So down here, your work, you have to decide on this thing. It's still going to be F dot dr. But do we want to throw that negative sign or not? Well, it depends. If you want to go that way and you want to think of this as a potential energy that you're storing into the object by elevating it, then you need that negative sign. That's why physics books always have this negative sign. You know what I'm saying? But instead of thinking like that, I want you to think like this. You are doing the work. Okay? So you are somehow exerting the force, Star Wars force, upward to match this gravity and pushing this thing up. Then how much work do you have to do to store this potential energy at that height? So that's what that negative sign is. So let's not get too hung up on that negative sign. So all we have to do is calculate dr and then substitute, eh? Okay, let's do that. So dr now here is equal to negative r sine t plus r cosine t. Oh, by the way, physics people, what do you want this potential energy to be? Plus h over 2 pi constant. Did I forget all these ij's and k's? Yes, I did. See, this is what happens if I try to solve something and then talk at the same time. But physics people, what is your potential energy at height h?
MGH.
MGH, right? And then did your physics teacher tell you that this is independent of the path? Doesn't matter if you directly elevate it or you go in a slant or go in a spiral even. That's why I picked spiral just to prove a point. We want this answer to be MGH, right? Yeah, okay. So that's that. So dW, which is F dot dr. Technically, you have to substitute all these things into the function f, but f is a constant function, so we don't care, right? So we are dotting this thingy with 0, 0, negative mg. You know what I'm saying? So this thing dies, this thing dies. Only thing we have is negative mg h over 2 pi, eh? And then the vector notation, when you take a dot product, disappears. This is it, isn't it? Say yes. Now, so if we take negative of the integral, that negative sign cancels this negative sign. So from 0 to 2 pi now, and you have that integrand mgh over 2 pi dt. You know what I'm saying? And this thing becomes, of course, mgh over 2 pi t evaluated from 0 to 2 pi. And that cancels 2 pi, so this gives you mgh, which is the answer you want. Dang, amazing, isn't it? Okay. The thing about this vector integral is this. Generally, this is true. If you have integral and C1 f dot dr, right? Let's say that C1 and C2 and C3 has a same starting point and ending point. So here's a picture. So here's the starting point. Let's say that is C1. Let's say this is C2. And then let's say that's C3. Right? So just like the case that we saw, this is C1, C2, f dot dr, same vector field all over the place. We're just taking three different paths, and if they turn out to be the same thing, right? So this thing is saying, independent of the path, right? Some kind of field, I like that. In this case, gravity, right? And most fields in physics happen to be independent of the path. Then we say this force, the field, force field, is conservative. Your tornado is not a conservative field. And you can see if you go this way, it's not the same integral as going the other way. You know what I'm saying? Because that thing has rotation in it, right? So tornado is not a conservative field, but most field that naturally happens in physics, such as gravity, electrostatic field, and whatever, they happen to be conservative field. Good? Okay, having said that, say we have such a weird looking field, the weird looking curve. Yes? Question?
Is a magnetic field conservative?
A magnetic field is also conservative.
Okay.
Say we have this kind of weird curve. And in that direction, here's the starting point and also the ending point. You come back to the same point. You know what I'm saying? So the integral of f dot dr guess what that is? Remember, we came back to the same point. Let's go back up here and Stairway to Heaven. Somehow we spiraled up, and then let's say we spiraled down to that starting point. What is the work or potential energy that we store into that system? I didn't hear that. There was too much static. You guys are trying. I think you're trying to say zero, right? This is how the conservative field works. If you come back to the original position, you get nothing, right? You gain some and you lose some, right? Think about this. If you release something from this point, because of the gravity, it's going to spiral down, but roller coaster, like, you can make it go back up to the, if there's no friction, you don't lose any work, then you can go back to the original position. You get it? So there's that, and we can prove it later, but that's how these things work out. And here's a weird symbol. People put circle around it, and you see that a lot, just to denote that this is an enclosed curve. Okay, and then convention is it's a counterclockwise rotation if it's enclosed field. If it's the other clockwise notation, people actually do these kind of things, arrow going the other way. You know what I'm saying? Otherwise, unless otherwise stated, all of the rotation is counterclockwise, positive.